Hello everybody, and welcome to Functions and Their Inverses Part 2. So recall that we talked about the definition of a function. We said that a function is a rule that assigns each input of a set D, called the domain, to a unique output of a set R, called the range. So graphically, we think of a function as passing the vertical line test. So that means, like, if I have any x value here, then it should only touch a single y value on the graph, right? Each input x should only have a single output y corresponding to it. So if we had a graph that looked more like this one over here, this would not pass our vertical line test. If we tried to draw a vertical line here, we'd see, oh, well, this x value hits two y values. This is not a function. So what we want to do here, as we talked about in the last video, we want to be able to use the idea of inverse functions to solve equations or analyze properties of functions. And we're trying to find an operation that allows us to get a natural definition for what an inverse function would be. So that operation is called composition. So definition, the composition, and we use this open circle, this open dot. It's not like a multiplication dot that would be filled in. It's, you leave it open. Of two functions, f of x and g of x, is defined as f composed with g of x is f of g of x. What that means is that you take the function f of x and you replace its input x with the entire function g of x. You plug in all of g in place of the x in f of x. So, to understand this operation, let's go ahead and look at these examples. F of g, or f composed with g, we've been given f of x is 2x plus 7, and g of x equals 3 to the x. So f of g of x means take the function f and plug in g of x. Now I'm going to break this into like tiny steps. So what I'm going to do is take everywhere there's an x for the function f of x and replace it with g of x. That's 2. Instead of x, I'll write g of x plus 7. But g of x is 3 to the x, so we can write this as 2 times 3 to the x plus 7. Now you should always, when you plug in composition, always put parentheses because you may have to distribute some terms and you want to be careful with your order of operations. But in this case, we see this is just a simple multiplication. We can clean this up by writing 2 times 3 to the x plus 7. Now for b, it's g composed with f. Well, that's g of f of x. So I'm going to take the function g, that's 3 to the x, and instead of writing x, I'm going to write f of x. Now let's actually plug that in. F of x is 2x plus 7, so this is 3 to the 2x plus 7. Well, I'm not going to really be able to do anything meaningful with this, so I can just write this as 3 to the 2x plus 7. It looks fine like that. Now for c, f composed with f, let's see what happens to the function f when we compose it with itself. Well, that's f of x, which is 2 times f of x, all plus 7. So if I substitute the original f of x in there, that's 2 parentheses 2x plus 7 plus 7. And now we see why we've been careful with this parentheses, because this time I need to distribute. It gives me 4x plus 14 plus 7. That's 4x plus 21. Okay, great. So hopefully this is a refresher, and you mostly remember this from algebra. But we see that, okay, we've got this operation called composition. And the idea is that you just plug one function into the other. So, okay, if this is our operation, we would need to figure out what an inverse would be and what an identity would be, right? And we need to know it's associative, and we need to know that it's closed, that the functions that have these inverses will, compose to give other functions with inverses. But I'm not going to worry too much about that. I'm going to focus on how do we figure out what a natural identity function would be and what a natural inverse for each function would be. So let's take a look. By definition, the identity would have to satisfy that f of I of x is equal to f of x, right? Remember, what is an identity? An identity is the thing that when you operate it, a star I gives you a. So f composed with I gives you f. Well, what would the function I of x need to be? There's really only one option. It should be pretty natural, right? If when I plug in I of x, I just get f of x, well, it's got to be x. So naturally, I of x is just the function x. So, by definition, an inverse function of f, written f to the negative first power, it's not a power, to be clear, this is just the notation we use. An inverse function of f must satisfy that f of f inverse of x equals x, and that f inverse of f of x equals x. That's the definition that we're talking about here, right? Remember, an inverse element in a group has the property that a star a inverse equals I. We said that the identity function is x. So for functions, the identity is x. So if we compose functions that are inverses, we have to get x. Now, while I'm on this topic, I want to point out something really carefully. This notation here, this does not mean 1 over f. This is the biggest, most common mistake I see students make, and one of the reasons why I think it's so important to spend time on this idea. This to the negative first notation, we use that to mean inverses. That's why we have the same notation for both functions and for multiplication, right? So like 3 to the negative first is 1/3, because, like, we use the same notation because 1/3 times 3 is 1. They're inverses, right? These are inverses. So we use that notation, but these are multiplicative inverses. For functions, we're talking about composition inverses. They're inverses under this new operation where we plug functions into one another. So that's the important difference, right? Really want to understand that this is just a notation for inverses in composition, and this is what it means to be an inverse in composition. That when I plug the inverse into the function, I get out x at the end. Okay, so we're going to consider some necessary restrictions, right? If we remember when we talked about multiplication, we couldn't include 0 with the rational numbers. Well, we can't include every function when it comes to inverses either. So, first let's look at this example. We're going to try to confirm that f of x equal to 2x plus 7 and f inverse of x equal to x minus 7 over 2 are inverse functions. So how do we confirm that? We're going to check f of f inverse of x. Well, if I take f, that's 2 times, and I plug in the inverse, x minus 7 over 2 plus 7, what do we get? If I multiply this across, the 2 over 2 cancels. I get x minus 7 plus 7, which is x. Well, that's good. Now I got to check out f inverse of f of x. So if I plug in f inverse into here, what happens? 2 oops, parentheses. So now I'm replacing this x with f of x. So that's 2x plus 7 minus 7 all over 2. So that's 2x plus 7 minus 7 cancels. That's 2x over 2. 2 over 2 cancels, and I get x. So these are inverse functions. When I plug either function into the other in place of its variable, I get back just x. And so that brings us to the big question. Do all functions have inverses? Well, I already spoiled it. They don't all have inverses. The question is, what does it take for a function to have an inverse? So we're going to consider what restrictions are required to guarantee that a function has an inverse. Okay, so let's consider a function f of x here, written in a table form. So this x is my inputs, y is my outputs. So when I have the input 1, my output is a. When input 2, output is b. Input 3, output is c. So based on this inverse definition, what happens? If I take f inverse of f of 1, I have to get 1. And f inverse of f of 2 has to be 2. And f inverse of f of 3 has to be 3. Okay, well, what's f of 1? Let's look at this first one. F of 1 is plug in 1, get a. So that means this is the same thing as saying f inverse of a is 1. So now we can look at what the chart looks like for f inverse. My input is a, and my output is 1. Same thing here. F inverse, if I plug in f of 2, that's b. F inverse of b is 2. Input is b, output is 2. And finally here, f inverse of f of 3. F of 3 is c. So it's f inverse of c is 3. So input is c, output is 3. Now look, this is my function f of x, and this is my function f inverse of x. What's happened to my inputs and outputs? Well, they've switched places, right? My input and my output each switched places. Okay, so inverses switch inputs and outputs. That's another way to characterize the inverse, right? They switch inputs and outputs. So then what could cause a problem with trying to find an inverse? Well, let's look at another example. What if my function f of x had x goes from 1 to y is a, x goes from 2 to y is a, x goes from 3 to y is c. So input is 1, output a. Input 2, output a. Input 3, output c. This is a function. That's fine. But if it had an inverse and switched inputs and outputs, what would happen? Well, if I switch these inputs and outputs, then my supposed inverse function would have an input a with an output 1, and the input a would also go to output 2. But that's not a function. It has one input for 2 outputs. And by definition, that's not a function. So now we see what the natural restriction has to be. That a function has an inverse only if each input only has, or each output only has a corresponding input, right? Each of these outputs, A, B, and C, only had a single input, which meant when we switched them, each of them only had a single output. On the other hand, if the same output appears twice for a function, then when you switch inputs and outputs, you'll get something that isn't a function. Okay, so we call this property one-to-one. It means for each output, there is only one input that corresponds to each. So the formal definition here is that a function f is one-to-one if for any two elements x and y, f of x equals f of y if and only if x equals y. Now, that may seem like a weird way to phrase it. What this means is if you have the same output, it was because you had the same input. They couldn't have been different inputs, or it's not one-to-one. Right? So like in this example, Well, the only way f of 1 and f of, so if I have a is equal to b, if those two things are the same, then the input must have been the same. But that, of course, seems odd. It's the useful way actually to express it in order to prove things in further topics. We're not going to worry too much about that. We do think graphically of this property as the horizontal line test. So it looks something like this. If I draw any horizontal line here, it only touches the graph one time. But on the other hand, if I look at a graph like this, this is not one-to-one, right? Because it touches the graph at the same output at two different corresponding inputs. So this is still a function. It passes the vertical line test. It's just not one-to-one because it doesn't pass the horizontal line test. Okay, so now we have the basics of what we need to talk about this operation composition. We say the operation of composition forms a group on the set of all functions which are one-to-one. In other words, if a function is one-to-one, we know it has an inverse. That's the really important thing. And it is also important that since functions and their inverses trade inputs and outputs, that means they also trade their domain and range, because that's what domain and range describe, the set of inputs and the set of outputs. So if f, the function f, has a domain A and a range B, then f inverse has domain B and range A. Okay, so now we're going to express this in the form of two equivalent definitions. So these two properties that we've talked about are fully equivalent to one another. Our original definition was let f be a one-to-one function, then its inverse, denoted f to the negative first, or f inverse, is the function that satisfies both f of f inverse of x is x and f inverse of f of x is x. Or version 2 of this definition, let f be a one-to-one function, the inverse of f, denoted f to the negative first, so to speak, is defined by f inverse of y equals x if and only if y equals f of x. In other words, the function and its inverses switch inputs and outputs. Okay, so now that we've gone through this thoroughly, we have all of the tools we need to thoroughly understand what a logarithm is, how it relates to the exponential functions. So hopefully this has given you a good background, and thank you for watching.